Imagine you are watching a rocket being launched toward a black hole with your enemy on board. As the rocket approaches this enigmatic abyss, gravity begins to act in surprising ways. Instead of accelerating, as you might expect, the rocket seems to be slowing down. The anger your enemy was showing, shaking his fist at you, also seems to lessen, as if stretched by time. As the rocket nears the event horizon, the boundary of a black hole where not even light can escape, something even stranger happens. Your enemy and the rocket appear frozen in time. They don't disappear immediately, but to your eyes, they seem still, motionless in space. What was once a vibrant view begins to fade, with the colors turning increasingly redder until, finally, everything vanishes. But what is really happening here? From the outside, to an observer like you, time seems to slow down more and more for anyone falling toward the black hole. This phenomenon is known as time dilation, predicted by Albert Einstein's theory of general relativity. At the exact moment the rocket crosses the event horizon, to you, it seems as if time has stopped. However, from the perspective of your enemy inside the rocket, time continues to flow normally, and he continues his journey toward the singularity, the central point of the black hole where gravity is so strong that the laws of physics as we know them no longer make sense. Einstein's theory of relativity leads us to some incredibly strange conclusions. It not only predicted the existence of black holes, but also their opposites, white holes, and even the possibility of parallel universes. These ideas might seem straight out of a science fiction book, but they are derived from mathematical equations that have been rigorously tested over the years. Imagine space-time as a large rubber sheet. If you place a heavy ball in the middle, the sheet curves around it. Now, if you roll a small marble on the sheet, it will circle around the heavy ball, just like Earth orbits the Sun. This curvature of space-time is what we call gravity, and it's exactly what happens around a black hole, only on a much more extreme scale. These curves in space-time are so intense around a black hole that nothing can escape, not even light. If you were near this boundary, you would see space-time distorting in ways that defy our understanding. The idea that time could stop, that light could be trapped forever, and that we might even find other universes by crossing this boundary is one of the most fascinating in modern physics. But how did these ideas come about? To understand, we need to go back to the turn of the 20th century, when Isaac Newton's worldview still dominated science. Newton imagined gravity as a force that acted instantaneously at a distance, as if Earth and the Sun were connected by an invisible string. But this idea, though revolutionary in its time, left many questions unanswered. For example, how could a force travel instantaneously across great distances in the vacuum of space? Newton himself admitted he didn't know the answer. It was Albert Einstein, about 200 years after Newton's death, who brought a new vision. He proposed that gravity wasn't a force acting at a distance, but rather a curvature of space-time caused by massive objects. To illustrate this idea, imagine you are standing on a trampoline. If you place a bowling ball in the center, the trampoline's surface curves around it. Now, if you roll a marble on the trampoline, it won't move in a straight line, but rather in a curved path toward the bowling ball. This is how gravity works in Einstein's view. The Sun curves space-time around it, and Earth follows that curve, keeping it in orbit. Einstein's vision was confirmed by observations and experiments throughout the 20th century, completely changing our understanding of the universe. But as with many scientific discoveries, each answer brought new questions. One of the most intriguing is what happens when the curvature of space-time becomes extreme, as in a black hole. The math behind black holes reveals a bizarre and counterintuitive world. Inside the event horizon, time and space seem to switch roles. To an external observer, time seems to slow down as you approach the horizon. But for someone falling into the black hole, nothing seems to change. The singularity, where gravity becomes infinite, is a place where Einstein's equations can no longer describe what happens. Some physicists believe the singularity could be a passage to another universe, a wormhole connecting two distant points in space-time. Let's consider a closer example to help understand this idea. Imagine you are walking up a very steep hill, so steep that it almost feels like a cliff. As you reach the top, your steps slow down, and it feels like gravity is getting stronger. You try to take another step, but something strange happens. It seems like you can never reach the top. This sensation is similar to what happens when trying to cross the event horizon of a black hole. From the outside, it seems like you are frozen in time, but inside the black hole, you continue your journey into the unknown. Another example, think of a fast-flowing river. If you place a small leaf in the water, it will be carried by the current. Now imagine the river is heading toward a waterfall. The closer the leaf gets to the edge of the waterfall, the faster the current becomes. Eventually, the leaf is pulled by gravity and plunges down the waterfall. A black hole works in a similar way, but with space and time flowing toward the singularity, like water flows toward the waterfall. Nothing can escape this immense force, just as the leaf cannot escape the waterfall's plunge. But if black holes can exist, why don't we see white holes or wormholes in the universe? The answer might lie in the extreme conditions required for these objects to form. A black hole forms when a massive star collapses under its own gravity after exhausting its nuclear fuel. The force of gravity overcomes any other force trying to prevent this collapse, leading to the formation of a black hole. But for a white hole to exist, we would need to reverse this process, which would imply violating several laws of physics, such as the second law of thermodynamics, which states that entropy, or disorder, in an isolated system always increases. Wormholes, on the other hand, are theoretical solutions to Einstein's equations that could, in theory, connect two distant points in spacetime. However, for a wormhole to be stable and traversable, it would require an exotic form of matter with negative energy density, something that has never been observed in nature. This exotic matter, if it existed, could keep the wormhole open, preventing it from collapsing under its own gravity. Without this matter, any wormhole that formed would collapse instantly, making it impossible to travel between universes or distant points in space. Nonetheless, the idea that white holes, wormholes, and parallel universes exist continues to fascinate scientists and science enthusiasts. Even though we have never directly observed these phenomena, the mere fact that Einstein's equations allow for their existence is enough to make us question what else the universe might be hiding. And to be honest, the history of science is full of examples of things that were once considered impossible, but eventually were discovered and confirmed. For example, black holes, which are now widely accepted, were once considered impossible by many scientists. When Carl Schwarzschild found the first exact solution to Einstein's equations describing a black hole, he himself was surprised. Many other physicists at the time also doubted that such objects could actually exist in the universe, as they would require an enormous amount of mass concentrated in a very small volume. Even Einstein wasn't convinced that black holes were real. It was only decades later, when astrophysical observations began to reveal objects behaving consistently with black holes, that the scientific community accepted their existence. Another example is the discovery of gravitational waves. For a long time, the existence of these ripples in the fabric of spacetime, predicted by Einstein's theory of relativity, was considered unlikely to be detected due to their weakness. However, in 2015, LIGO, a physics experiment in the United States, directly detected gravitational waves for the first time, once again confirming the accuracy of Einstein's predictions and opening a new window for observing the universe. These examples remind us that science is constantly evolving and that the impossible of today might be the established fact of tomorrow. So, even though white holes, wormholes, and parallel universes might seem like pure science fiction, we can't completely rule them out. But for now, what we can say for sure is that black holes exist, and are one of the most fascinating phenomena in the universe. They challenge us to rethink our understanding of space, time, and the very nature of reality. And you? Would you be willing to launch yourself toward a black hole to discover what lies beyond the event horizon? Do we have enough courage to face the unknown and explore the limits of our understanding? Leave your thoughts in the comments. After all, science is a continuous journey of discovery, and each new question brings us a little closer to the answers we seek.